All right. Idea of heap sort. Now we are at this point. Yeah. The point is we build a max heap. Okay. So given an arbitrary array, yeah. So first we run the max heapify operation. Building the heap. Yeah, actually, not just max heapify. Max heapify is a local operation. But building a heap, that's a global operation. Yeah. So we run that, building a heap, that operation. So we get a max heap. The cost, bigger of n. So that cost is, not very high. So we can take it, yeah, that cost. Now, let's do the heap sort. Now we want to get an ordered array from max heap. Yeah. A key observation. Yeah. So let's look at this diagram. Yeah. We assume this diagram is a max heap for the given array. We complete the building step. All right. Then there is a simple property in this max heap. The maximum value must be at the root, right? Yeah. Based on the property of max heap, the largest element is at the root. Yeah. The next question, if you know the largest element is at the root, yeah, what can you do to put it in place? Yeah. Because our goal, if we know the element at the root, yeah, if we look at the original array, that is at the root is at a location with index 1, right? So that's the root. Yeah, because we do not use the 0 location. Okay? Yeah, we use the index starting from 1. Well, the root is there. Then our goal, we want to put all the elements in place. That's our goal. To sort the whole array, that means we put all the elements in place. Now we know the largest element is at the root. We can put it in place first. So the first thing, let us put that root in place. In place, it's in place location, the end of the array, right? That's the in place location for the maximum. Yeah. That means to put it in place, we need to do a swap operation. One swap operation will put it in place, right? Yeah. Yeah. So look at that. Yeah. So root is at the beginning of the array, yeah. But we want to put the, the end of the array. Yeah. So that means one swap. When we do one swap operation, we can make it. Yeah. Just one swap operation. Very easy. Yeah. But the problem is, after you do one swap operation, you change the structure of your max heap, right? Yeah. Yeah. After that swap, then the current heap won't be a max heap anymore. Yeah. Yeah. It violates the max heap property. So you need to recover it. Yeah. Recover it. Yeah. All right. But the violation only occurs at the root, right? Yeah. Because other places you do not touch. So the max heap only occurs at the root node. Then you can run, max heapify operation. You only need to follow, do the max heapify starting from the root, but when you move the dirty node, now the root node is dirty. When you move down the dirty, you follow the path all the way down to the bottom. Yeah. Yeah. Leaf level. So then, after that max heapify operation, you recover the current heap to a max heap. Yeah. But you need to, do the max heapify operation. After you recover the max heap, the next step. Now, the second largest element is at the root, right? Current root. Second largest element at the current root. Yeah. And the second largest element should be in this position, right? Because the in place you can eliminate from the consideration. Yeah. So then the current last element, the current root should go to the current last element. Another swap operation. You put it in place. Okay. Then, because there is a violation of the max heap property, you do max heapify from the root. Another round. Every time max heapify swap. Yeah. So let's do it in this way. Okay. After we get a max heap, first we do one swap operation. Okay. So one element is in place. The largest element is in place. Then after that, max heapify. Then another swap, second largest element in place, max heapify. Another swap, the third largest element in place, max heapify. Yeah. Keep doing things like that. Then at the end, we get the whole array sorted. Yeah. That's the whole idea of this heap sort. Yeah, this is a heap sort. Yeah. Yeah. But remember, our three requirements at the beginning. One requirement, in place, right? We want to have this sort must be in place sort. When you have in place sort, we should avoid using the recursion. We should avoid using recursion. If a recursion, you have a deep stack, then it won't be in place algorithm. Yeah. So all the steps, max heapify, all the steps, you should use the for loop or while loop. Yeah, for loop, because if you do not know how many levels to go, then you need to use a while loop. Yeah. Okay? While loop, you check condition. If you do not reach the leaf level, then you keep going down, right? When you start from the current node, right? While loop, keep going down. Yeah. Every time you can reach one of the child nodes, yeah. Keep going. Yeah. Yeah. All right. Yeah. But when you hit the leaf node, you know how to detect the leaf node, right? Yeah. When you hit that leaf node, then, yeah, so you complete that max heapify operation. Yeah. But the building heap, you also need to use the loop to implement. Do not use the recursion to implement loop. Yeah. Build a heap. Yeah. Try to use the while loop to implement. In that way, so you make your whole algorithm in place. Yeah. So that is important. Okay? All right. Keep in mind. Yeah. Yeah. Although some people, they tend to use the recursion implementation because that is easy. Yeah. That is much easier. Recursion, well, you can write a pretty short recursion implementation. But if you want to have the true in-place algorithm, you need to avoid using recursion. Yeah. All right. Yeah. So here you can see how to do the heap sort. Yeah. Operation. Yeah. So we write a pseudo code when we start swap A of 1 and A of n. Yeah. Then recover the heap structure. Yeah. All right. Max heapify. All right. Yeah. All right. Yeah. So there. Yeah. Yeah. Procedure of heap sort. Yeah. Iteration. Yeah. First, we build a max heap on this array A. Yeah. We call a function to build that max heap. Yeah. All right. After that, then we do that swap, max heapify that one. Yeah. Swap A of 1 and A of I. Yeah. Because I going down from n down to 2. Yeah. Yeah. Every iteration we reduce that value I. Yeah. Yeah. Here we use a for loop. Yeah. So here we use a for loop. Yeah. All right. Swap these two elements. After that, we reduce the heap size. Yeah. All right. Then we run max heapify on array A at the root 1. Yeah. 1 index for the root. Yeah. After that, then we move to the next iteration of this for loop. Yeah. Yeah. All right. But in this simple code, yeah, if you really need to get an in-place algorithm, you need to make sure you build a heap, max heap function should be implemented without recursion. Your max heapify function you should avoid recursion. Then the whole algorithm, you do not use recursion. You can make it in place. Yeah. All right, so that's the heap sort step. Yeah. After that, analysis, efficiency analysis. Yeah. All right. From the diagram, so let's see what is the cost of the max heapify, because every time after one swap, you need to do max heapify. Yeah. So the most of the work you need to do max heapify. Okay. Yeah. All right. But we need to estimate. Yeah. When you do max heapify, when your heap size is n, because when you start, your heap size is n. Then when you do max heapify, the operation you need is log of n. Yeah. Log of n. Okay. Yeah. Number of levels you can approximate by log of n. Yeah. It's a ceiling function log, but here we just move the ceiling function. Yeah. It's still very close. Yeah. All right. Then the next max heapify operation, because the number of the heap size becomes n minus 1. So the next round, max heapify, we need log of n minus 1, approximately. Okay? All right. Then you just add up all these log numbers. Yeah. That's the estimate. Yeah. Next, how to estimate the summation of these log numbers. Summation. Yeah. Very easy. When we do summation, each term less than each one. Yeah, so log of I less than or equal to log of n, right? because your I, the largest I is n. Other than n, all the other i's less than n. Yeah. Yeah. So here we use this less than or equal sign. When you add up all these numbers, there are n minus 1 terms, right? N minus 1. But we use n terms. How about that? Yeah, we use more. Okay. Now you can see the estimate will be bigger of n times log of n. Yeah. N times of log of n, that's our goal. Yeah. Yeah. So we get the efficiency function that satisfies our requirement. Our requirement, we want to get an n log n algorithm. Yeah. And this is the worst case. This is the worst case. The worst case is n log n. Yeah. 3 requirements. Yeah. Worst case, n log n. It satisfies that important requirement. Yeah. So the in-place requirement, worst case n log n requirement, and supporting dynamic data, right? Yeah. Dynamic data. Yeah. In the binary search. Yeah. 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 Maintain your dynamic data efficiently. Yeah. Yeah. So that part, yeah. So the detail we skip. Yeah. We skip. Here we have the structure, right? Yeah. So how to manipulate data is, yeah. We need to do some more work. Yeah. To make sure we maintain dynamic data efficiently. Yeah. Yeah. All right. Yeah, actually here you can see, actually, it's not that hard to maintain dynamic data. So we need a smart way to maintain the dynamic data. All right. Yeah. Next, then, I want to talk about this important topic. B.4, lower bound for comparison sorts. First, this term. What's the comparison sorts? Yeah. So there are comparison sorts and non-comparison sorts. Non-comparisons. First, I want to explain this concept. Comparison sorts and non-comparison sorts. All right. Comparison, the basic operation is the comparison operation. You rely on comparison to sort your array. Yeah, that's simple. But there are some special sorts. You do not rely on comparison. You do not do comparison. Okay? You can get all the elements in the array sorted without doing any comparison. But you do different operations. So here, I'll give you one example. One example for that. That's called a counting sort. You do operation, you do counting. Counting is different from comparison. Yeah. Count, 1, 2, 3. Yeah. Incremental, yeah. Counting. So it's called counting sort. no comparison. Yeah. For the counting sort, yeah, then it's not the general, it's the special. Because counting sort, you need a lot of conditions in order to do counting sort. You need to, there. You need to follow some conditions. Yeah. Yeah. For the general sort, you know, usually you do not have any condition. Yeah. Given array, an array of numbers, then you can do the sorting. Okay? Yeah. But for the counting sort, in order to apply the counting sort, you need some important conditions. All right. The first condition you need to have integer data. Okay? The data must be in there. Yeah. For comparison, you do not require integer data, right? Floating point, you know, arbitrary data. So the first thing is integer data. Why integer data? Because it's very convenient to count. It's friendly for counting, right? Yeah. If you have floating point data, then it's hard to do counting. Okay? Yeah. All right? Yeah. So easier for counting. Let me explain why easier for counting. Yeah, yeah, because that example, that idea is very simple. All right. Let me explain why the integer data is easier for counting. Okay. All right. Suppose we have an integer array. All right, so here, let me see. Integer array. And integer array. Integer array means array values are integer. So, you know, a of 0, a of 1, yeah, a of a, n minus 1, all integers. Okay, all right. Then, so the next, yeah, you need to do some assumption. Yeah. All right. You need some auxiliary array. Auxiliary array. Yeah. Here, let's assume C array as the counting array. That's the auxiliary array, okay? C. And auxiliary for counting. Okay, all right. Then, for these integers, the range is important. Yeah, the range. We need to use the use the range for counting. Okay, all right. The range for counting. Okay, all right. Then here, to show you the idea, okay? So let's assume the range. The range from 0 through k. How about that? The range. Now, integer numbers, yeah. If they're different from this range, can we do some mapping, okay? Do some simple mapping to map it to some range. Yeah. But it should be simple mapping, yeah. Not very complicated, okay? Yeah. So here, if we use, if the range, the values in this range, then now we do the counting, okay? All right. So first, in a for loop, we go through all the elements from 0 through n. For loop, I from 0 to n minus 1. Okay, all right, for loop. All right. Then, first you need to process first element, a of 0. A of 0 takes the value in the range, right? Yeah. A of 0, is it in this range? Yeah, based on our assumption. Yeah. Then we need to count, because a of 0 equals some number. We want to know how many elements in a array have the same value as a of 0. We want to do that counting, okay? All right. So C of A of I plus. See, the counting element, yeah, counting array, but counting array, which element we want to count? The value of A of I. If an element equals this value, we increment the counting number by 1, right? So in this way, yeah, so this C of this particular number, that's the counter, stores how many elements in A array have the same value. Okay? Yeah. Yeah. So we run through the whole. So we have a C array, have all the counting numbers. Yeah. No comparison, right? We only do the counting. Okay? All right. After that, we have this auxiliary number. Then, our destination array, that's B array. Okay? B array is the destination array. So we will put the elements in place, okay? Yeah. So A array, original array. Yeah. Go. Put the elements in place to get a B array with the help of auxiliary C array. Sorry. Because we get a C array. Okay, all right. With the help of C array. Okay? Yeah. Using information stored in C array, the counter, yeah, then we can put the elements in A array in place in the B array. Yeah. Yeah, that's easy. How many elements have 0? Yeah, the idea is very easy. Okay? All right, the first block, we pack all the elements equals the value 0. Okay, all right. Then, the second block, value 1, all the elements that take value 1. Yeah. So, with auxiliary array, we can put in the B block. Okay, we just calculate, you know. Yeah. The algorithm is pretty smart. Here, I skip the detail. Okay, just give you the, you know, high-level description. Okay, doing that. Yeah. And the last block, K. How many elements? You know, so we pack. Yeah. Yeah. In this way, we can sort the array, yeah, by counting. No comparison. Yeah. So that one we do not. That algorithm is a non-comparison sort. Okay. Yeah. So here we do not study those special sorts. Yeah. All right. So integer. Yeah. The first requirement must be integer data. Second requirement, the range. Yeah. Because the range. The range must be in bigger of n. Bigger of n. Yeah. If the range is too large, then the performance will be very bad. If the range is too large, performance will be very bad. So the range must be bigger of n. Then the performance efficiency is also bigger of n. So that's very fast. Yeah. So that counting sort, yeah, under some special conditions, you can make it very fast. All right? And it's not comparison sort. Okay? Yeah. So here, the reason I want to give you this example, just let you know, not all sorts are comparison sorts. Yeah. Some sorts are non-comparison sorts. All right. Then, but the topic of this one, B.4, we want to study comparison sorts. Yeah. All right. Yeah. So now we study the comparison sorts. Comparison. Yeah. All right. Yeah. So here I do not need to give you a definition, so you know the meaning. Yeah. Comparison sorts. All right. Then I give you the conclusion first. This formula I gave you before. I remember I wrote once before, yeah, because it's a long time ago. Yeah. So let me write it again. Okay, all right. So the conclusion. Yeah. All right. Yeah. Any comparison sort for arrays with n elements. Okay. Requires at least this many comparison, the ceiling function, log base 2 of n factorial this function comparisons for the worst case. That's the conclusion for the worst case. Okay? All right. Yeah. That's the conclusion. Yeah. This formula. Okay? Right. Yeah. So you can see, yeah, by this formula, first, 4 factorial, okay? To sort 4-element array, that is 24, right? Seeding function is 5. 5 comparisons. The minimum number of comparisons to sort a 4-element array, 5. Yeah. All right. Then, look at the 5 factorial. 127. To sort 5-element array, the minimum number of comparisons, 7. Yeah. 6. To sort 6-element array. Okay? Yeah. Greater than 9, less than 10. So it's 10. Okay? Yeah. All right. And so on. Okay? Yeah, here. Yeah. So this number we call the lower bound. This is the lower bound function. All right. Yeah. The lower bound, so you cannot do better than the lower bound, right? So the first question, question 1. Yeah. Nobody can do better than the lower bound. Lower bound. Okay, the first question. Second, is it possible to find an algorithm to give you the efficiency that equals the lower bound? Yeah. So, for given n, okay? Question: can you always find an algorithm that sorts an element array with this many comparisons? Answer this question, okay? Yeah. This question, currently, this question, unknown. unknown. Okay? Yeah. We know we may do slightly worse than the lower bound. But if we can do exact as the lower bound, then that is unknown. Okay. We can do slightly worse than the lower bound. Okay? Yeah. But exact lower bound, then we don't know how to. So next question, how to see this lower bound, right? Yeah. Yeah. So we can answer that question. It's the lower bound. Yeah. All right. To understand that, the question, how to get that lower bound? That lower bound number. We answer this question. So there is we need to use a special method here. Yeah, so here I need to introduce a special method. It's called a decision tree method. Decision tree method. We need to use decision tree to study all the comparison sorts. Okay? Yeah. So the goal, so we use, what's decision tree? I need to explain. We need to use the decision tree to study the comparison sorts. Yeah. All right. So first, I need to describe that decision tree. Yeah. Make a decision. Yeah. Decision tree. You draw a tree corresponding your comparison decisions. Yeah. When you do comparison, okay? Yeah. So let's because it's a tree, there are many nodes in the tree, right? Many nodes. So decision tree is a binary tree. Yeah. So each decision tree is a binary tree. It's a binary tree. Corresponds to decision. Yeah. So what kind of decision? So in each node corresponds to one comparison. To one comparison. All right? Yeah. Specifically, let's A colon B, yeah, means we compare A and B. Yeah. When you compare A and B, you make your decision. Yeah. Based on the comparison results. Yeah. Two possibilities. Left branch, when A less than or equal to B, we go to the left branch. Okay? When A strictly greater than B, we go to the right branch. Yeah. When you use this way to draw a binary tree, we call it decision tree. Yeah. for your comparison sort, because you need to have a comparison sort first. When you run your comparison sort, you need to make a sequence of comparisons, right? Then you can draw a decision tree corresponding to your comparison sort. Yeah. Yeah. Let me show you one example. Yeah. So that one example, so we sort 3-element array. 3-element array. Yeah. Okay. Yeah. Sort. Yeah. Example. Let's do example. Sort 3-element array. Okay. Yeah. 3-element. Let us use ABC. So we compare AB first, okay? Yeah. So get it sorted. Yeah. All right. Then, we try to insert C into a sorted array. Comparison, okay? All right. Yeah. Yeah. Let me draw that decision tree. Yeah. All right. Yeah. Here, yeah, we use insertion sort. To sort 3-element array. A, B, C. Yeah. Now I want to show you how to draw that decision tree. Yeah. So you get an idea how to draw decision tree. Yeah. All right. When you start this insertion, so you compare A and B, right? So that's your first comparison. So we put as a root node, okay? A:B, then you have two cases. The first case, A less than or equal to B, then second case, A greater than B. If A less than or equal to B, what is your next comparison? Because A, B ordered, so your C comparison insert into ordered array. You need to compare C and B, right? Yeah. So B:C. B:C, you have two cases, right? Yeah. First one, B less than or equal to C. The second, B greater than C. All right? Yeah. The first case, B less than or equal to C. Can you already get the array ordered? Yeah. Sorted? Yeah. So we reach the leaf node. So we use this rectangle shape to represent leaf node. Yeah. So in the leaf node, we have A less equal to B less than equal to C. That's the order. Okay. All right. Then let's go to, if B greater than C, we need another comparison, A and C, right? Yeah. So another node, A:C, yeah. Two cases, A less than or equal to C, and A greater than C. Yeah. When A less than or equal to C, can you get the sorting result in the leaf node? So, because A is smallest. Okay? All right. Then A is less than or equal to B, B greater than C. Yeah, C. Yeah. A less than or equal to C, and C less than B. So that's your sorting result. Okay? All right. Then this case, A greater than C, so C is the smallest, less than A, less than or equal to B. Okay? Yeah. All right. Then this side, A greater than B, yeah, B smallest, A largest, right? So you need to compare A and C next comparison. Okay? Yeah. Compare A and C, then two possibilities, A less than or equal to C and A greater than C. Yeah. Right. A less than or equal to C, then you have it sorted, right? Yeah. Sorry. Yeah. C, A, yeah. A, yeah, because A greater than B. B is small, yeah. So here you get it sorted. So we can write a sorting result. Because B is smallest, less than A less than or equal to C. We get a sorting result, okay? A greater than C, then we need to compare B and C. Yeah. So B less than or equal to C and B greater than C. B less than or equal to C, B is the smallest. The sorting result is B less than or equal to C less than A. Right? Yeah. And in this case, B greater than C, C is the smallest. C less than B less than A. Okay. So this is the decision tree for insertion sort on three element array. Okay. Yeah. So I use this example. I just want to make this point. Yeah. For any comparison sort, if you have a specific algorithm, then we can draw decision tree for your algorithm. Okay? Reflecting all the comparison details. How about that? Okay? No exception, right? Yeah. Then you can see, based on this example, we can use a general decision tree to study any given comparison sort. Yeah. 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 All right. So, yeah. So any comparison sort has a decision tree. Okay? Yeah. Then we studied the decision tree. Okay. Then when you have a decision tree, what is the worst case? Yeah, because our goal, we want to consider the worst case. What is the worst case? Efficiency. Worst case. Okay? Yeah. Three comparisons here, right? Yeah. So here the worst case, three comparisons. Each edge is one comparison. Three comparisons. Okay? So, this case, two edges, two comparison, but it's not a worst case. Okay? Yeah. All right. So this is worst case. This is worst case. Okay? All right. Yeah. So the worst case efficiency, that corresponds to the height of the tree. The height of the tree, okay? Yeah. Because you look at the longest path, so that's that height of the tree. Yeah. All right. The number of edges on the longest path. Yeah. So what do you mean the height of the tree, right? It means number of edges in the longest path from the root to a leaf. So that's the worst case. Yeah. Now, we want to show the worst case is greater, equal to that number, okay? This number. The height, okay? The height number is greater or equal to this log of n factorial seeding function. All right, so now let me show, yeah. So I think I should have enough time, yeah. So 10 minutes, let me use 10 minutes to show this, okay? So the goal, show that h, now you know h, greater or equal to okay, all right. So we draw arbitrary decision tree. Okay, yeah. Arbitrary decision tree. So here, it's very hard to draw the tree precisely, right? Yeah. So we just draw, some general shape. Okay? Something, general. Okay? All right. Then, one thing. We estimate the leaf. Capital L represents the number of leaves in this decision tree. Yeah. The first question, how many leaves do you have in this tree? Yeah. So you know the meaning of leaves, right? So the nodes without any child, that's the leaves. Number, yeah. Actually, for those leaves, remember, we use the boxes to represent the leaves, okay? Internal nodes, we use circles. The leaves, the bottom level, we like to use the, boxes. Because in the leaves, we need to write sorting result, okay? Sorting result, yeah, inside the leaves. Oh, sorry. Oh, yeah. Keep. Yeah, I want to keep. Yeah. By accident, I get out of it. Now I need to play it again. Yeah. Yeah. Let me change the pen color. All right. First, let us estimate number of leaves. How many leaves do you have here? How many possible sorting results? N element. All different orders, all the possibilities, different orders. How many? Is it, permutation? Permutation of n numbers, is that? Yeah, because any order is possible. So the permutation of n, is it n factorial? Is it n factorial? Yeah. Because number of permutations of n elements, that's n factorial. Okay? All right. But this n, we say n is greater or equal to n factorial. Yeah. So we do not write n. Yeah. There is a possibility n equal n factorial, but n, in the general case, n is greater or equal to n factorial. Why? Because you may have the redundant sorting result, right? Yeah. Your algorithm is not the, most efficient. So it may contain some redundancy. If there's redundancy, some same result repeated more than once. So then you have more than, greater or equal to n factorial. But it cannot be less than n factorial. Yeah, because you need to cover all the sorting possibilities. You cannot have less than n factorial. So greater or equal to n factorial. All right, that's one thing. The second thing is we have another. So what is the relationship between little h and capital L? The height and the height of a binary tree and the number of leaves of the binary tree. So there is an inequality. 2 to the h greater or equal to L. So this inequality. Let me explain. Let me use 3 minutes to explain this inequality. How can you see it? Okay, the question, how to see it? There is an easy way to see it. Okay? There is an easy way to see it. Okay? What's that easy way? Let us consider a complete binary tree with height h. How about that? Consider a complete that complete binary tree. With height h. Okay. Yeah. When we say complete binary tree, that's among all the binary tree with height h, the maximum number of leaves, right? Yeah. So this kind of binary tree, so this binary tree, okay? This kind of binary tree, complete binary tree, okay? This complete binary tree has the maximum number of leaves for those with height h. Because complete binary, the bottom level is full. So no missing nodes. Packet, all nodes filled in the bottom level. That's the maximum number you can have, right? But that maximum number is 2 to the h. Okay. The maximum, okay? But our decision tree, in general, it's not a complete binary tree, right? So then the number of leaves should be less than or equal to this number. Cannot be more than this number, okay? So that means that greater or equal to capital L. Then capital L greater or equal to n factorial, right? All right. Then in this inequality, we take log base 2. Okay? We take log base 2. So we get h greater or equal to log base 2 of n factorial, right? This capital L, we use it as a stepstone, okay? Stepstone between 2 to the h and n factorial. Now, we skip that stepstone, okay? Then we take log base 2, we get that. But h is an integer. Integer greater or equal to this non-integer expression, log base 2 of n, so we can take the seeding function. Also true. Also true. Okay? So in this way, we should, h is the worst case number, right? So h, we know from the previous slide, the worst case number. So now you know the worst case number of comparisons always greater or equal to seeding function of log base 2 of n factorial. Okay. You prove it. Yeah. this decision tree method. Improve it. You can see it's very powerful. This decision tree problem solving tool. We treat it as a problem solving tool. Okay? Yeah? Because when you consider comparison sorts, most of the comparison sorts is unknown, right? Yeah, they're unknown. Yeah, most of comparison sorts. So we only know finding small number of sorts, right? Yeah. Selection, bubble sort, insertion, merge, quick sort, heap sort, counting sort. Only 7 here. Yeah. But you have, huge number of various sorts. We cannot call their names. And most of them are unknown. But we can still study unknown sorts through this decision tree tool. We can study unknown. Yeah. Because we know the number of leaves, we can estimate. The height, we can estimate. And we have conclusion, lower bound. Yeah. All right, so I spent a lot of time explaining this. Then, in the final, I will give you questions based on this formula, right? Yeah. Actually, in your homework assignment too, you already have a few questions, right? Yeah, because I gave you this formula before, okay? Yeah. I didn't prove it, okay? I told you, yeah. There is a lower bound function. Yeah, I remember in one lecture, yeah, I give you that. But I said I will delay the proof later sometime. Yeah. So now today, I complete the proof. Yeah. Okay. Yeah. So in the final, you should have 2 or 3 questions. You may need to use this formula. Okay. For example, if I ask you, can you use 12 comparisons to sort 7-element array? Yeah. Then this formula, you calculate. You need to calculate 7 factorial and see, is it bigger, smaller than that 12? Yeah, it's 13 actually. It's 13. 13 means you cannot do better than the lower bound, right? So your conclusion, you cannot sort 7-element array by 12 comparisons. Okay? Yeah. Question like that. Yeah. No, you apply this formula directly. Yeah. Okay. Yeah. All right. Yeah, we run out of time. So, 1 minute past the time. Yeah.